Thank you. Welcome to the special invited seminar on phase array radar. Professor David Schvartzman from OU. He was born in Brazil, got his undergraduate degree in Paraguay, adjacent country, moved to Paraguay for 7 years old, I guess, much younger. Then he got his master's and PhD from OU. He has industrial experience, worked at NSSL, interpreting radar data, signal processing. He has basically interfacing radar data with the atmospheric measurements, converting measurement scientific products, signal processing. He has a very all-round experience with the phase radar. Given the phase radar, so new, not that many people have that much experience working in this area at this point. So he's been here in this area on a different project. He said he's available for just today and tomorrow to give a seminar he selected for today. I'm glad you are able to make it on a Thursday afternoon. Today's talk is about fully digital phase radar. Our radar, what we're going to be building today, we are working on this A part, is a hybrid radar. It's an analog or digital combination. It scans in one dimension digitally, other dimension analog. But this is a fully digital array, the fascinating technology, a ground-based radar. About that is going to be a presentation today. Thanks, Dan.
Well, thank you. Thanks, Vivek, for the invitation and the introduction. And thank you all for coming and participating. My talk today is titled Advanced Capabilities in Atmospheric Science Applications of the Fully Digital Horus Phased Array Radar. I'll be telling you all about the Phased Array Radar program and what we've done with Horus at OU. Before I get to actually show you the Horus data and some of these cool new scan modes, I'll talk a little bit about what phased array is, how it works. It may be trivial to some of you, but just to make sure we're all on the same page, I'll just cover a few quick basics. I'm a professor in the School of Meteorology, but also affiliated with the Advanced Radar Research Center and the School of Electrical Engineering. My background is in electrical engineering, but I apply to radar meteorology. Okay, so I'll just start quickly explaining how we came up with looking into phased array radars for meteorological observations. The key here is that science is driving the technical decisions that we made to come up with this type of instrument for meteorological observations. The first question we ask ourselves is, what is the observable scatterer? What type of particle do we want to look at? In our case, for weather radar, it may be rain or snow. For cloud radars, that could be cloud particles. And so, and what is the desired observation range? So when we ask that question, that determines the scattering, physics of it, the attenuation, and the sensitivity that we're going to get. And so that dictates the wavelength of the system that we're going to use, transmit power, and antenna gain. Okay, for weather radars, typically we use S-band, C-band, and up to X-band. The next question is the observable scatter geometrically complex? So does it have variation in the two dimensions? For the case of weather radars, yes. Particles can have different shapes and different orientations. And so we require polarimetry. Now we transmit two waves, horizontal and vertical. Could be simultaneously or could be in alternating mode. We want to understand better the aspect ratio of the particles and the shape of the particles. Third question is, within the observation range, what are the spatial scales of interest? So we need good spatial resolution. For that, we might need good bandwidth for the range resolution part, and a large antenna size that will determine the beam width or the angular resolution that we will scan with. And then, do we need fine or adaptive angular sampling? That maybe will determine if we can use a mechanical scanning instrument like a dish radar or a phased array. And then the last question here is, are the atmospheric processes rapidly evolving? Do we need high temporal resolution? That again dictates the difference between a mechanical or an electronic system. If things are evolving really fast and we use a mechanical large, 2-ton antenna, we might not be able to keep up with the scans or the volume scan times that we want. And so we might need something that can scan faster. And this is coupled with the previous question, right? How many points do we need to sample and how fast? The lower the coverage, the faster we may be able to sample, but typically we need 360-degree coverage and also go up in elevation. So many of these atmospheric observational needs naturally lead to polarimetric phased array radar. That might be somewhat obvious to everybody. Now, what are the different severe weather events that can impact society and kind of motivate everything we're doing? Of course, tornadoes, flash flooding, hurricanes, hail, damaging winds, lots of fatalities caused by these severe weather events, and also lots of property damage every year. And there's a lot of papers quantifying the impacts of severe weather. I don't think I need to convince you guys of this or tell you much about this. I think you all know this. And so from that point of view, weather radars are exceedingly important to answer fundamental questions about tornadoes, flooding, hail, all kinds of severe weather that impact us and society in general. And they're happening now more and more everywhere in the country and the world. So this is an example of a devastating EF5 tornado. You may be familiar with this. It happened in May of 2013 in Moore, Oklahoma. It resulted in 24 fatalities and injured 212 other people. It cost over $2 billion in damage estimated for now. So this data you're seeing here is from one of our dish radars, surprisingly. This is from a polarimetric X-band radar called PX1000 that collected the data in 2013. So you may be wondering, how is it getting such high temporal resolution observations? So these are taken at 20 seconds temporal resolution, but the trick here is that the antenna was only scanning a single elevation angle and scanning fairly fast. Okay, so we lost all the vertical structure and all the vertical information of the storm just so that we could observe fast enough and show how rapidly a tornado is changing. That was the point here. But of course, vertical structure is really important. And we can't just say, okay, when there's a tornado, we'll just scan the lower level. That's not going to work. So then we look into phased array radar and compare that to dish radar systems. So there are some comparisons here left and right, as you can see. The main advantages of the phased array radar technology are that we have superior temporal resolution. Maybe we can bring down volume scan time from 5 minutes to, let's say, 15 to 20 seconds, using different tricks and techniques, capabilities that one of these systems has. We can form hundreds of beams, let's say in the vertical dimension, for example, and get very fine sampling of a storm vertically, reconstructed vertically, let's say as the antenna rotates mechanically in azimuth. So we can rotate once and collect a whole volume of data in 10 to 15 seconds. So there's other benefits on the right here, some of the capabilities that only phased array radar can provide. The top one shows focusing. So maybe we have a way of determining some regions that are more important than other regions in the storm. So with this capability that I'll show later called electronic steering, we can just look at the more important regions more frequently and occasionally maybe look at the less important regions. We can do something called space-time multiplexing. We can start looking at regions multiplexing between one or the other to improve the data quality. And then lastly, this bottom one says imaging. We can transmit a really wide beam of energy and then capture all the signals that are scattered back to the radar within that transmit beam, within that wide beam of energy. And so we call this imaging because it's using the radar kind of like a digital camera. You illuminate a really wide region and then you sample all the energy coming from that region instantaneously. There are some trade-offs, of course, but only phased array radar technology allows us to do that. And so here's some observations from a phased array radar that was built in the ARRC a long time ago, in 2011 or so. This is from the atmospheric imaging radar. You may have heard of this, called the AIR. It was a very simple imaging radar mounted on the back of a truck. And it collected these data from the El Reno storm on May 31st, 2013. This is real data. And the colors there are showing isosurfaces of reflectivity. I think the red colors are 50 dBz's, the orange is 40, the yellows are 30 dBz, and the greens are 20. But this is only reflectivity. It's not even Doppler or any of the other variables. We can already see, because the scans are about 10 seconds for full volume, we can already see some really interesting features in the storm. For example, right around here, you can see a very fine line that looks like where the updraft is lifting all the humidity and the raindrops, and then the hail core might be located somewhere here. So we can gain a lot of information by having three-dimensional observations like this one from a phased array radar. Current radars only scan a few elevation angles as well. And so we lose a lot of information of the complex structure of the storm vertically. Okay, so what other science can phased array radars enable? Obviously, high temporal resolution observations that can allow us to look at lightning and storm electrification. I'll show an example of observations of plasma reflection from lightning with Horus later today. Fine scale observations of tornadoes, microphysics, boundary layer type of research. Maybe it can be coupled to improve numerical weather prediction models, all kinds of different things. If we couple the phased array radars with a network of passive radars on the ground, we can also retrieve 3D winds using this technology. This can also be done with dish radars, but it would be more effective with phased array. So all kinds of applications. How does phased array radar work? Well, most people already probably know this. You can think of it as, in the left image, as a ripple tank. Imagine you're on the side of a pond, you have two rocks in your hand, you let go of both rocks at the same time. Two concentric waves start propagating outwards, right? And when these waves start interacting, there are different things that happen. In this center line here is where we get maximum constructive interference. Constructive interference between the two expanding waves. Some of these other lines, we also get constructive interference. The wavefronts are aligned, like you see in this bottom right figure, and then the sum of the two creates a higher peak. And in some other regions, maybe we get destructive interference. And so the whole idea is that we want constructive interference to form our main transmit beam, and then some of the other interferences that we'll see here form what we call side lobes or nulls in the antenna pattern. But this is the basic principle. Of course, we're just talking about 2 points here. A phased array antenna may have thousands of these little antenna elements. And so it's like you're throwing 1,000 rocks at the pond all at the same time. Or maybe you change the time. So if you think of only having 2 rocks and you let go first of one and you wait a little bit and then you let go of the other one, now the circles will expand at different times. And that will concentrate this maximum constructive interference in a different direction. So that's pretty much the basic concept. And so this illustrates a little bit more detailed what we call phased array beam steering, which is essentially what we were just talking about. In this bottom image here, you see several of these antenna elements is what is represented at the bottom, and then the waves that are transmitted by each of the antenna elements. If they all transmit at the same time, then we form a beam that has the maximum constructive interference at broadside, which is the center. Then some of these other regions with constructive interference are what we call the side lobes. And then where we have destructive interference, we have these nulls, these deep places where there's no energy radiated in those directions. If we change the timing of the transmission of these signals in between the adjacent elements, like you see in this case, now the wavefronts are not aligned, but they form a line in a different direction. And so the constructive interference is actually steered in a different direction. And so just by changing the timing at which we transmit the signals out of each of the elements, we can steer the beam. In a radar, you do that by changing the phase of the signal. I'll have a little example here in a second. But essentially, this little equation, very simple, tells you if you want to steer a beam in the direction theta, which is this angle here with respect to the broadside, you have to apply this phi, 2 pi d sine of theta over lambda. Lambda is the wavelength, and d is the distance between the elements, which is normally half of the wavelength. So then you apply this phi sub I, delta between each element, between adjacent elements, and you steer the beam in the direction you want. Okay, pretty easy so far. So these movies show how these sinusoids that come out of each of the elements have different phases and align the wavefront for propagation in a different direction. It's essentially what's happening. And just a nice little animation that shows how this works. Now, what else can we do with the antenna pattern? If we optimize the excitation that we plug into each of the antenna elements, we can also change the shape of the antenna pattern. We can change the shape of the energy that we radiate in space. So here we have what we call a narrow beam, which is what we get, a pencil beam, which is what we get when we put the exact same signal in every element. we can come up with a way where we can lower the side lobe levels by changing the excitation. But there has to be a catch, right? It's not always free. The catch here is that we lost some resolution. The beam width is a little bit wider. So we can push the side lobes down, but we give up a little bit of angular resolution, the beam width. Okay, what else can we do? Maybe we have a strong target in a certain direction that's contaminating the measurements in the main lobe, and so we can put a null in a certain direction adaptively. You can say, oh, there's interference coming from that direction. Let's put a null, not transmit or receive any energy from there so that we don't contaminate our measurements. And the other thing we can do is widen the beam, or spoil. We call this beam spoiling, intentionally broadening the transmit beam. And that's this imaging concept I mentioned earlier, where we transmit a really wide beam of energy, then we receive from all directions at the same time. So now the question is, how can we use these capabilities for meteorological observations? Well, the first and most obvious thing is we can do this electronic beam steering. The point here is to scan two different directions or two different regions. We don't need to waste any time scanning in between them. So we can scan one region and then jump directly to the other region of interest. With a dish, you can't do that. You're mechanically rotating, you have this inertia, you can't just stop and jump to the next point. Here, without any moving parts, you can say, okay, steer in this direction, scan here, stop, steer in this direction, scan here, done. Okay. Another thing we can do is this beam spoiling. We can change the shape of the beam, illuminate a wider region, and so now we can collect all of these data, in this example here, at the same time that we would a single beam. So we can speed up the scan. If we spoil the beam, let's say by a factor of 5, now we can collect 5 times the sector width in the same time that we would with a normal pencil beam. So we speed up the scan by a factor of 5, essentially. And then the last thing we can do is we can have something we call dual flexibility. So in some regions where there's nothing, maybe we can scan fast, just send out a couple pulses just to make sure nothing new appeared. And then where we have storms or any returns of interest, spend a lot more time, get better data quality and all the good things we want. So a lot of different capabilities. Now, not everything can be done with every phased array radar. Phased array radars can be built in many different ways. And this, I know this is kind of a busy slide, but it shows different types of phased array radar architectures. On the far left, we have this one, which is the simplest one. Essentially, everything is analog in the antenna array, and then we only have one transmitter and one receiver, very similar in some ways to a dish past the array itself. And then in each element, we have something we call a phase shifter and an attenuator. So with this architecture is the simplest one, and this already existed in the 1970s. We can electronically steer the beam, and that's about as much as what we can do, some dual flexibility. But we can't do beam spoiling or any of these other more advanced modes. We can build an array that's frequency scanned. Okay, now we can change the steering angle, changing the frequency. Maybe it allows some fast scanning as well. It's relatively simple, very low cost. Similarly, we can build an array that has a separate transmitter and receiver. We call this fixed imaging. Excuse me. We have a fixed transmit beam. We cannot change it. It's always this same transmit beam. Then we form multiple receive beams independently. Okay. It's also simple. It can allow fast scanning, but it's very limiting in some ways. We can have something called a subarray beamformer, where now we take groups of elements and we digitize the output, inputs and outputs of groups of elements. And so the idea here is that we're digitizing at different levels. On the far left, pretty much everything is analog except for the input and output to the whole array. On the far right, we have what we call an all-digital beamformer. So in this case, every single antenna element has signals that are digitized on transmit and on receive. And this is the most advanced architecture you can build. This is as far as you can go in terms of digitization for the elements. Essentially makes a software-defined radar, if you will. You can reconfigure the array, you can change how it operates, you can subdivide it in different subarrays and say, for example, this group of elements will look at that part of the sky, this group of elements is going to look at this part, all kinds of different combinations. Because of this and the huge potential of the fully digital phased array technology, that's why we decided to pursue this concept and we created the Horus program that started in 2016. Horus is the Egyptian god, the god of war and sky, the all-seeing eye. You know, we had to give some kind of catchy name to the radar, and this just kind of resonated, made sense, stuck, and so we called it Horus, but there's no other special meaning. It's just the name of the Egyptian god for the all-seeing eye. And it's not capitalized. Sometimes people think it's an acronym. Type it all caps. It's not caps. So the Horus is a mobile, fully digital polarimetric S-band radar. It can operate as a rotating phased array radar, or it can also operate stationary. It was developed to demonstrate the potential of phased array technology for meteorological observations, mainly with funding from NOAA. And with the fully digital architecture, this system allows extreme scanning flexibility to evaluate different array scanning modes. And I'll show you different scanning modes here as we go along the slides. The array currently has 13 array panels fully populated, which are the ones you see on the right picture. In the yellow contour, it shows the 13 panels that we currently have, are these 13 here. That is when we had the array in a large anechoic chamber and we were calibrating it. It produces a beam width of 3 degrees in azimuth and elevation, which is not optimal for science in general, but it's a demonstrator system. And because it's mounted on a mobile platform, we can get really close to the storms and still get really good observations. It's been operational since 2013, and we've collected several data sets since then. So I'm going to show you a lot of data sets that we've collected with Horus and kind of talk about the benefits and the reminder of the talk. So first off, you watch this movie maybe here. That was during a supercell storm event we had in Norman, April of 2023. We collected data in this mode where the array was rotating mechanically and transmitting a spoiled beam vertically. Now in the bottom charts, you see here, that's an RHI scan, just collecting vertical columns, range height indicator, and it's showing all 6 polarimetric radar variables. And then here's another scan, I think from the same day, October 4th of 2023. These ones are collected with 1 second temporal resolution. So it's only one vertical scan. It's not a whole volume scan. In this case, just one RHI, but 1 second per scan.
How many angles?
In this case, 64 beams in elevation. Okay, so this is what we would call pencil beam. Pencil beam is the simplest type of operation, right? We're not doing anything like beam spoiling or any complicated scan. Now, briefly talk about polarimetric calibration before we move on to more data. Polarimetric calibration of phased array is probably one of the most challenging aspects of this technology as of now. It's the main reason why we haven't completely adopted the technology for operational use in the country and in the world. We're still trying to figure out how to calibrate the radar to get accurate polarimetric measurements. So on the left here, you see some measurements we got when we had the array in our anechoic chamber after we had conducted calibration. So what these measurements are showing here in the top, we have this probe, S-band probe, tilted 45 degrees, transmitting, and the array is receiving on all elements at the same time, horizontal and vertical polarization. So what you see here is the phases that are measured in the array when the probe is not moving. It's just at the center, geometric center, transmitting at 45 degrees. And so the concentric circles are showing essentially the phase of that wave propagating and being measured across the array. That's what you would expect. And it's wrapping over 2 pi as it goes outwards. So if you run some unwrapping of the phase, that's what the bottom plots are showing. Now you see something that looks like a simulation, but I kid you not, this is real measurements. So this is after we ran calibration techniques for the radar. One benefit that this system, the fully digital radar, has is that we can apply something called mutual coupling calibration, where one element talks and all the neighbor elements listen, and then by looping through all the elements in the array, the system can self-calibrate itself. Because of the geometric position of all the elements with respect to the others, we can take advantage of that to apply a calibration concept and then automatically calibrate the system. And this can take 10 to 15 seconds, this self-calibration concept. And this shows a little bit of what we get when we run the mutual coupling, the right image here. So the one on the left is the initial measurements we got when the array was in the chamber. Mutual coupling can be done in the field, in situ, and we get the measurements like the ones you see in the bottom here. So every element talks, all the neighbors listen, and then we can use the information received by all the neighbor elements to calibrate the one we want. Okay, so after running this mutual coupling calibration, we conducted some measurements to verify that the beam had the right shape. Measurements were conducted using a UAV platform, a drone. This picture on the left is just to show the radar and the drone close to each other. We were not taking any measurements here. We were taking the measurements when the drone was 140 meters away. And it was flying over this surface of a sphere in 2 dimensions. And we collected this middle pattern that you see here in the bottom chart. So you compare the simulation, the measurement, take the difference and zoom in the beam width. Pretty close, plus minus 0.15 dB or so from the simulation. So after getting these measurements, something that looks like a textbook type of picture or a simulation, we thought, okay, the radar is well calibrated. We can go out and start getting good weather data. We also compare the copol and crosspol, something that happens in dish radars as well, but it's less of a problem, is this cross-polar contamination. We transmit from the horizontal and vertical simultaneously, and part of each of the two contaminates the other. It leaks. So when we transmit H, it also, a little bit of V comes out, and the opposite happens for V. So we have a little bit of this cross-pol contamination. We don't like that, and we try to mitigate it because it's contaminating the measurements we are trying to get. So you see the two copol patterns are shown here, H and V, and the cross are in the diagonal, in the cross diagonal. This chart here shows the difference in dB, or the ratio in linear units, between the H and the V beams. It's trying to see how well matched are the two beams. So if you take that difference and just look inside of the beam width and average all of this, which is what hits the hydrometeors, comes back and we average in the radar, mismatch is about minus 0.0278 dB. Okay, still pretty happy with the calibration. We thought, okay, let's move forward. Now there is one problem. It's this crosspol that we were just saying. So how do we mitigate crosspol? There's this technique that's fairly new. We recently implemented and we're testing it with Horus now. It's called the cross-polar canceller, or XPC. What's the idea? This is just a small subset of elements, just to illustrate. They're all transmitting H and V, and they also have their cross-pol components, which are these little arrows, cross H, cross V. What's the idea? The idea is that we can use a subset of elements as canceller elements, and we transmit the opposite of the crosspol by the canceller elements. And then we can put nulls in the crosspol antenna pattern and reduce it even more. So this is another benefit of a fully digital array. You can dedicate some subset of elements to do crosspol cancellation or side lobe whitening or all these kinds of things. So in our simulation, this here shows how the crosspol canceling works as you steer the beam off the broadside. So you have a copolar pattern here, a crosspol here. This is not using the XPC technique. And then in the bottom here, you can see what happens when you use the XPC. You put a null right in the center of the crosspol, and then this shows one cut of the antenna pattern. The red plot shows the crosspol and how it has that null in the center. The green one is the original crosspol. And as you can see here also on the bottom left, at the beginning, we only use one canceller element. As the array is steered away, we need more power. And so we add more elements to continue canceling crosspol. What's the trade-off? Well, when you use some of these elements, instead of using them to transmit your copolar intended polarization, you use them to cancel, you lose some gain on transmission. So every element maybe costs you 0.25 dB of sensitivity.
You also change your main beam too.
You also change the main beam, so you need to recalibrate. Yeah. So everything in the radar world comes at a price. But we're trying to combine all these tricks to figure out how to use this advanced system. So these are just some more results from this XPC technique. We have a very recent paper that came out. You can look it up and read more about it. I don't want to dive too deep in the details. But the idea is, as you steer more away from the center, from broadside, and you go especially to these corners, you might need 4 or 5 canceller elements. And then here in the bottom on the left is the biases that we would get with Horus. without using XPC, some biases in Z in reflectivity, biases in differential reflectivity, ZDR, some biases in the correlation coefficient, ρHV. When we use the XPC, the cross-pole canceller, most biases go away. There's still a little bit left over. It's really hard to really mitigate everything, but it's a lot better. So right now we are actually demonstrating this technique with the radar. We implemented it and we're collecting data to write a paper demonstrating it. Okay, so let me show you some actual data collection examples. This one is another RHI scan. We have reflectivity, Doppler velocity, spectrum width, and correlation coefficient here. I'll highlight that we are using this technique called PPC, progressive pulse compression. When you use this pulse compression technique to increase the sensitivity of a system, you may have something called a blind range, a portion where you don't see. Recently, one of our students came up with a way of mitigating that, called it progressive pulse compression. So despite here we're using pulse compression, we can still see in the blind range. These data were collected with 8 seconds temporal resolution over about 15 minutes, and you can see some of the sampling parameters here, 128 pulses and 1 millisecond PRT. So it looks pretty convincing, very smooth. These data were collected on February 16 of 2023, right when we started deploying the radar more regularly and when it became operational. At this point, we were not doing anything super fancy like spoiled beams or crazy things. We just wanted the simplest type of scans and verified that things were working. Then we did some quantitative evaluations, some plots here of histograms of reflectivity and correlation coefficient to show most values are between 0.98 and 1, which is what you want for raindrops. In theory, they should return correlation coefficients of 1 exactly if everything is perfect, the raindrops are spherical, the volume is filled with perfect spherical raindrops. Normally, we measure 0.99 or so due to the noise and practical imperfections, but anywhere along that range would be fine. ρHV is a very important variable for a lot of algorithms, and it's a good discriminator to evaluate if your beams are well matched and if your radar is working well. So this was an initial quantification we did. And then the other thing we did in these bottom histograms you see here, we took the first few scans from the previous data that I just showed in the previous slide. First 5 scans, averaged them, subtracted from the next 5 scans, averaged, and then we made these plots that are of the differences between the 5 scans averaged before and after, just to quantify the standard deviation of the errors, and to see, well, we got a Gaussian curved, zero mean, about plus minus 1 dB standard deviation. That's dictated by the number of samples in the PRT that we're using. Everything looked good. Similar curve for ρHV. Okay, this gave us more confidence. Things are working well. Here's the example I promised earlier where you see this is a return from plasma reflection from lightning. Dish radars have observed lightning before. This is not the very first observation from a plasma reflection. But because dish radars are scanning relatively slow with respect to lightning, which happens in the order of tens of milliseconds, maybe a couple hundred milliseconds, then you may see just a few range gates, maybe just a few pixels of a lightning flash. Now, with a phased array, you can see much more than that, much more structured to the lightning. And in this case, the dots that you see that are plotted in the movie dynamically are detections from the Oklahoma lightning mapping array. And so we're validating that we can detect lightning with rapid scanning phased array, comparing it to detections from the lightning mapping array. Okay, this is something we were just starting to look at, thinking, okay, maybe in the future we can use phased arrays also to detect lightning and to predict regions that will have more lightning activity based on negative cores of KDP, specific differential phase. Anyway, in this case, the scan was taken every 1 second. And so the dots are mapped to this color scheme that you see here on the right. There's less than a third of a second span between all these numbers. The numbers are really long because essentially the same hour, the same minute, the same second. It's very little change in time. But it's showing how fast lightning is propagating through the storm. Okay, so then the next question is, everything so far looks beautiful. Have you compared it to a dish radar? Just try to run your phased array against a known dish, compare the data. Okay, we collected data with Horus and Raxpol simultaneously. I think this was August 8th of 2023, almost a year ago. Some of the scan parameters are shown here, but in particular, you can see the corresponding plots between Horus and Raxpol and here in the right panels. I should say these two radars are completely different. One is a phased array at S-band, the other one is a dish at X-band, different beam widths, different transmit powers. This was just a way of roughly validating polarimetric performance, but we should probably run it against another S-band radar that is comparable. We got some plots, scatter plots, comparing Horus and Raxpol. You know, things are not perfect, but looking pretty good. Relatively high Pearson correlations between the phased array data and the dish data. Okay, promising results. Not super convincing yet, but we're on our way. Now, this is all the pencil beam observations, calibration, some data examples I showed. Let's talk about more advanced beamforming modes. Let's talk about all the spoiled beams and more advanced things we can do with a phased array. So here are 3 examples of different transmit beams that we can use. One is we spoil the beam just in elevation. Maybe we just rotate and spoil in elevation. Maybe we can form 2 different peaks, each one spoiled, and do something with that. Maybe you're thinking, what can we do with that? Well, maybe we keep one of those 2 beams pointed at the lowest elevation, 0.5 degree or so. It's the most important one because it's what's coming to the ground. And then we use the other one to kind of go up and down and scan the higher angles. So we always get a scan at the low elevation angle, and then we get scans not so often, but less frequently, but everywhere higher aloft. And then the third one here is spoiled in 2 dimensions. So there's significant sensitivity loss when you do this, but you can scan the whole sky very quickly. This one is 20 degrees by 20 degrees beam width. So you can do the math and figure out you can scan the whole sky very fast with a beam this wide. So here's an example where we collected data with that type of beam, the spoiled in 2 dimensions. It's not 20 by 20. This one was an 8 by 8 spoiling. In the top, you'll see azimuth from 150 to 240, a 90-degree sector, in a 20-degree sector in elevation. The data are 3D in this case, right? So what we're doing here, just to illustrate, this top plot just shows the maximum power along the range. So we're looking into the storms and taking just the maximum value along range. This bottom one shows the lowest elevation PPI scan. So as I play the movie, you see 3-second temporal resolution scans. You can see little airplanes moving every 3 seconds, and you can see the storms around. So with this kind of scan, you can maybe think about a concept of multifunction where you're tracking aircraft and doing weather surveillance at the same time, maybe. I think this was the first time we tried the 2-dimensional spoiling. That was in January of this year. Since then, we've been collecting a lot more data using these advanced modes. I'll show you now some data from a hail core we observed on April 28 of 2024 with scans that are 3.5 seconds in temporal resolution. In this case, we had a total of 55 transmit beams. I'll show the scan in the next slide. And we were forming over 1,000 beams on reception. So digitally, using this concept called digital beamforming, forming over 1,000 beams on reception. So this is the scan, and where you see these colored dots in the scan, those are the centers of the transmit beams. The green line is showing how we rastered through the sector. We were going from minus 30 to 30 degrees in azimuth, 0 to 30 degrees in elevation. And this entire scan took 3.5 seconds. In this case, the antenna was not rotating. It was stationary, just pointing in one direction. Inside of these, this red square here, you see there's all of these little white dots. The white dots are the receive beams that we're forming. Ultimately, those are the data that we get. So wherever you see a white dot, we are getting 1 beam of data. So we have a lot of elevation scans and very well sampled in azimuth as well. It's like getting PPIs and RHIs at the same time, fully filled in volumes. Transmit beam is shown down here, and then this is the receive beam. The data ultimately is determined by the combination of these two things. In this case, we're trying to get good side lobe performance while still collecting all the data as fast as we could. And so here's some data, reflectivity here, Doppler velocity, differential reflectivity ZDR, correlation coefficient. Data at 3.5 second temporal resolution. The hail core obviously was located somewhere around here, and it was moving forward, closer to us. I believe the range here was about 50 kilometers or so from our location. And this is only a sample of a few minutes of the data collect. This is only showing one elevation angle. So I made a movie here that shows what we can do with this kind of data. So you see a transect through the storm here, and then I'll start moving this in the movie, and we will start interrogating the storm in different angles and different directions in 3D. Now, one thing I'll point out, this return you see up here is a fake return from side lobe contamination. So I'll talk a little bit more about this in the next slide, but obviously the storm kind of ends here around, 15, 17 kilometers, and then we have another return past 20 kilometers, likely not real. That's the ZDR, the differential reflectivity. We don't see any apparent biases. We don't see any problems with the data. So that's very good indicator that we are getting good polarimetric calibration. It's not demonstrated fully yet, but we think it's working pretty well. All the variables. This one is differential phase, the FDP, across the storm in 3D. Okay, and then using this tool, we did a reconstruction of the reflectivity in 3D, and this is illustrating the 3D isosurfaces of different reflectivity values around the hail core. And as you see here, now I'm going to filter the isosurfaces to look at just higher than 50 dBz, and then I think the pink one inside is 60 dBz. So then we can do a little bit more filtering. Hopefully, there we go. And now we're just looking at where we think the hail core is located in this case, in 3D. And obviously, we have data every 3.5 seconds in this case, so we can track the change of the hail core in volume and size, see what's happening with the storm as it's evolving. Okay, so I mentioned the side lobe contamination we had, and this is a downside of using spoiled beams. I'll tell you why. We want to get high temporal resolution. Okay, we think this spoiled beam concept is the solution. Cool. Then we also want to get very low two-way side lobe levels, 70 dB or some number like that. Okay, we also have to deal with some of these cross-pole biases and all these things. Now the challenge here is that using spoiled beams increases the side lobe levels, which is directly against our other requirement, which is getting low side lobe levels. So then the question is, how do we get the high temporal resolution and low side lobes at the same time? Why do we have this problem with the side lobes? Well, when we transmit a spoiled beam, we have a very high gain on transmission. On reception, we have this blue beam, and the two-way antenna pattern is the sum in dB, or the product in linear units, of the transmit and the receive. So your transmit is contributing 0 here. It's not helping you lower the side lobe levels. And the receive helps you lower it maybe 20 dB. So the resulting two-way pattern is minus 20 dB. No help from the receive beams. For one of these that is more on the edge, like the orange one, if we put it on the edge, okay, now the transmit has come down in power. So now we sum like minus 12 dB plus the minus 20 from the original receive beam, minus 32, lower side lobe. Okay, but that's only on the sides. In the center, it's not very good. So what do we do? Well, maybe we can design beams that have separate transmit peaks, like the ones that you see here. So this is kind of a new concept, generating a transmit that has 3 independent beams in different directions, all coming out at the same time. So this is something new we're trying now. We have here one that's spaced 7.5 degrees in between the peaks, one spaced 15 degrees in between the peaks. The more you space them out, the better it is, because then you get lower side lobe levels overall. You can push the energy lower the farther you push these out. There are trade-offs, as always. One thing you can do when you apply this concept is do something called deterministic beamforming. So we can put nulls in the directions of the other transmit peaks on reception. And so the two-way patterns can have very low side lobe levels, 55 dB, 45 dB practically. And so we can improve their side lobe performance a lot using a concept like this. On the left, this is a simulation that I did using ideal parameters. On the right, I added random element amplitude errors and random element phase errors that are based on actual measurements from Horus. And then the side lobe levels went up about 10 dB. So in the perfect world, 55 dB. In the real world, maybe 45 dB achievable with Horus. So you're thinking maybe, how can we use this concept for a real scan? So let me show you this movie that illustrates how you can use this. So there's your phased array. The colors are different beams, think of it that way, green, red, and blue. Now we start rotating and transmitting the three at the same time. So each one is covering a different sector. Question is, what happens when this blue one gets to that point? Now we start sweeping the exact same location, right? We're starting to scan what the previous red beam already scanned. We go up in elevation. Okay, we rotate more, we go up again, then we go back down. And so then up and down, this little concept, after you've rotated once, you can collect all three elevations at the same time. Interesting concept. Okay, well, we were thinking this is very interesting and very cool, but very complicated, right? You have to have everything very well synchronized, rotate, go up, go down, etc. With a fully digital array that can do two-dimensional steering, we thought, why not just offset the peaks like this? Instead of having them all lined up at the same elevation angle, just put them at different elevations and space them in angle, in azimuth. Then you just rotate once, no up and down, you collect all three elevations you want. So that's the next thing we did, and in this case, you see here the transmit beams, 0.5 degree elevation, 0.9 degree, and 1.3 degrees. So these are the lowest elevation angles that the WSR88D, the NextRad scans. That's why intentionally we put the transmit peaks in those directions. You rotate once, you get all three at the same time. We actually took Horus out and looked at a point target, collected data using this beam type to demonstrate and validate that it worked. So here's some real data from a point target. Three beams formed on reception, these are two-way, and we get about the exact predicted performance of 45 dB between the main lobes and when you start seeing the side lobes. It's interesting too, you see the nulls that are formed in the directions of the other transmit peaks. So we are trying to null out the energy on reception, and it seems to be working. Very cool. Does it work with actual meteorological observations? This is the next question everybody asks. Have you collected any data? Can you show more than MATLAB simulations? Sure. So here's one case, three beams in elevation, 2, 12, and 22 degrees, just so that we had, if you collect 0.5, 0.9, and 1.3, data looks very similar, because these elevations are very close. So we intentionally did the beams vertically, very spaced up, so we could see different data. So here's three scans collected simultaneously. In this lower one, there is some beam blockage. You see some of that up here. In the higher ones, no beam blockage. The data seems to look pretty good. We compare these measurements between Horus and KCRI, which is the prototype WSR88D in Norman, operated and maintained by the ROC, by the Radar Operations Center. We got these data, which are the processed moments, and took the data you see in the black box, extracted that specifically, very high signal to noise ratio, strong cores, and we wanted to compare statistically. Obviously, these two systems are very different. There's a lot of differences, but statistically, the data should agree relatively well. So we extracted the data in here, and then we made these histograms that show the data from Horus and from KCRI. The histograms are overlapped. Blue is Horus, and this orange color is KCRI. So things look, there are some little differences here and there, but overall the shapes are very similar, about the same, and they are in the same position. So this shows that this beam with the multiple simultaneous peaks seems to be working. So this is another alternative so we can get high temporal resolution, low side lobes, good data quality, etc. You may be thinking, what's the catch? What's the trade-off? There's always a trade-off. Whenever you do any of these techniques that you spoil the beam or divide the energy in different directions, you absolutely lose some sensitivity. So you have a finite amount of total power. If you form one pencil beam, you get your full power in that direction. If you form 3 of them, well, each one has a third of the power. You're just distributing the same power in 3 different directions. So now you lost some dBs, but you gained that you're scanning 3 elevations at once. Anyway, so with that, I'll get to the summary, and I have a lot of additional slides. If we have time and there's time for questions, happy to show more or talk more about anything I showed today. But just very high-level summary. Transformative science studies dictate the need for polarimetric phased array technology. Fully digital phased array is the most capable one, and right now we're using this Horus system to explore all the capabilities, different scan modes, see when using one type of scan is better than another one. Combining recent efforts, PARRC can simultaneously provide high temporal and spatial resolutions, observations with high data accuracy. It's kind of like this multiple transmit beam mode. Mobile Horus radar is producing what looks like promising polarimetric observations. It's ready for field deployments. If you guys have an idea or a project you want to go and try to collect data, contact us. Let's try to set it up. And we believe that this technology can really help unlock some fundamental uncertainties in the life cycle of precipitation systems in general and in different types of storms. So we're using it as much as we can to explore different types of meteorological applications. So anyway, with that, I'll thank you all again for the invitation, for your time, for participating. Happy to take any questions.
A nice presentation with a combination of science and engineering. Very nice display. And, given that it covers a lot in many range of areas we're talking about, I'm sure a lot of questions here. Particularly in the case of APAR or thermal phase radar, we're thinking about how do the polarimetric measurements that good? That is a big challenge. Given that what you demonstrated today, it's like, yeah, it is possible to do that in the airborne phase radar systems. With that, if you have any questions, please go ahead and. Okay, yes.
I've seen things like this. It's very impressive, and there are a lot of capabilities for sure. I wish you would have gone, when you were going through it, you would have pointed out all those things that are the negative. Like you said, there's always a trade-off. You've got to spread the beam out, you lower the sensitivity, your side lobes come up, and so you've worked a lot with that. I should have said that in the beginning. Is there, do you have a bag of gotchas or things that you should keep your eye out for, or some of the negative things? We're going to fall into that. We're going to make this thing work, and it has to work really well. And we need to know about those things that are going to be the holes we don't want to step in, so we can avoid that. So not necessarily we can go into it now, but that would be really great to have a list of things. You guys should look out for this. We found out that this is an issue, and all those types of things. Those are the types of things that will really help us get down the road.
Absolutely, absolutely. So I'll give you some ideas on these things. Let me go back to this one slide. So this one has some of the trade-offs explicitly listed in the bottom. Let me tell you a few more things that we are just finding out now. You have a phased array, it has these antenna elements, each antenna element. Each element has horizontal and vertical polarization. Okay, you're going to excite both or one at a time, get polarimetric measurements. Practically, the antenna pattern of the single elements of H and V are actually not identical, or not the same. So you transmit both or collect some data, then you try to compare. The beams might be offset, they may not be exactly the same. If you have a very narrow beam and you do a pencil beam, you might not see any biases. If you spoil the beam, you see the effect of the element pattern on your far field spoil beams, or any kind of weird beam forming you can do. It's one thing we recently found. What's the trick? What are we doing now to mitigate that? To form these spoiled beams, you have to come up with the complex beamforming excitations for each antenna element, so that when you generate the wavefronts in the far field, they sum up to be this distribution of energy that you want. If H and V are different, we thought, how about we come up with independent weights? A subset for H and a different subset for V, such that in the far field, the beams are matched. We get the beam width exactly the same, the gains the same, then you mitigate all the biases in the far field. So this is something new we're doing now. That's a big gotcha. You think, oh yeah, spoiled beam, H and V, cool, super easy. Get some data, then your Roy tree doesn't look very good. ZDR is very biased on the edges. Something happened. We found out collecting data, and then we came up with a way of compensating on transmission to match the beams. So lots of gotchas, of course. Happy to share anything we have with you guys anytime.
The lightning was interesting. What is the characteristic of the signal that shows up with that lightning?
Very interesting question. We are also investigating that, I should say. I have a project with the NSF for looking at lightning and storm electrification with phased array, and I have a student writing a paper on this topic. What we are seeing is reflections from the hot plasma. It's really hot plasma coming down with very high voltage, of course, and lightning. There's some scattering and reflection. Can we explain the physics of plasma? Not yet. But we see it in the polarimetric variables, and we are quantifying the changes, doing histograms before the lightning, during lightning, and after lightning. Increase in reflectivity about 7 dBz. Change in differential reflectivity. Reduction in correlation coefficient. We have some heuristics to know if we are getting plasma reflection in the data or not. My student is kind of getting into the physics of plasma, but he's becoming a little bit of a physicist at this point. We're trying to do some applied radar meteorology. So at this point, we can detect lightning with rapid scans, but I don't know that we can explain the backscattering from plasma on the IQ data.
So you're using multiple fields combined to give you that signature?
Yeah. Yeah, so when you use these beams, and I didn't show it today, I don't have pretty pictures yet because it's too new data, but when you use these 2D spoil beams and you're looking at some thunderstorm core, if you catch lightning and you catch the plasma reflection, you actually see the entire 3D structure of it coming down to the ground. And we already have a few cases of this. I don't have pretty pictures to show, and we just got the data from Earth Networks yesterday. That goes all the way down to the ground. But we have data where we show CG cloud-to-ground lightning from the cloud to the ground in 3D. You see the step leaders and the whole thing coming down. In one snapshot, but you have to scan it really fast.
So you have an LMA, right?
Oklahoma LMA, yeah. NSSL has the LMA, and they manage it. We are working with them and collaborating.
Yeah, interesting. Paris.
Yeah, so the image that I showed has detections from the LMA. So these dots are what the LMA detects. And so we're overlaying them on top of the lightning detection. And so we have a little algorithm that, based on the polarimetric signatures of lightning plasma, creates these contours where we think lightning is. So right now, in the research we're doing is we compare where we drew the contour based on radar data and where the dots from the OK LMA are. We haven't done it for the 3D detection yet, but we've done a lot of them in 1D, or in 2D, I should say.
I have a question. In the A part, we have the 4 panels, at least like the vertical wind. You can do that with R4 dual Doppler. I was wondering, have you considered, we have a space antenna where cross-correlating signal get a tangential wind. Have you tried that with this digital phase array so I can get an up and down drive? Tangential is not radial waves. Have you done that?
We haven't done it with Horus. We've done it with the passive radars and the WSR-88D, not in the same way, but kind of similar. But yeah, the idea is to try to measure Doppler from different angles and then get multi-Doppler, right? Is that kind of what you're
No, I
thinking?
thought
or-
in the SPY one before, I thought Dovia tried to do that.
Okay.
With the top elements, bottom elements cross correlate the signal. Then you get the tangents and when. And now if you're going to do that, maybe it's possible, I guess, that's big thing for APAR, to try to get the up and down draft as good as possible. Otherwise, we need to have this, top-looking radar to get a very good observation of up and down draft.
Very interesting. I actually honestly haven't thought of that or seen the paper. Maybe I should look into it and maybe we should try it with Horus.
Yeah.
And if that would be helpful to you guys, more than happy to run some
Because
experiments.
it's like you can separate the element return from two different halves like that and stuff. But it's something new, it makes fascinating to do it.
Yeah. Sounds very exciting. One thing I should say, go back to my slide with the scan. You see here, right now we are getting 26 simultaneous digital channels with Horus. So every panel, we sum up all those signals and record digitally that for H and for V. The radar is a fully digital radar. Technically, every element can save data, record, etc. If you do fully digital recording of IQ data, we don't do processing in real time, I do the processing after, 1.5 terabytes per second. So no one wants to deal with that, so I just said, just give me some preformed beams from the panel, and then I'll do some beam forming, there. We can, so for this kind of experiment, maybe we can, and the nice thing is you can reconfigure the array. So maybe we divide the top and the bottom halves in different things, and then.
Yeah, I thought that getting a tangential is the big plus in any measurements.
We could emulate APAR, essentially form digital channels in the rows
That's
with
right.
Horus.
Exactly, top off, bottom off, we have the 449, John showed that, worked on that. We have a system here, but then get the same kind of things like that, 4 megahertz. So, any other question on the web? Any other question, audience, still? Okay.
I have a question, but it might be a silly one because this is not at all a field of expertise. But when you're taking your measurements, you have moved the truck somewhere and parked it and it's stationary. Have you tried taking any measurements with it moving and looked at how that would affect? Okay.
No, typically we deploy in one site. This is a huge truck.
Yeah.
It doesn't look as huge maybe in the pictures. It's a semi.
Yeah.
You need a commercial driver's license to drive it. So I actually got my CDL a couple months ago. I know if this doesn't work, I can drive Amazon deliveries. No, we haven't. It's big, it's heavy. The antenna is also heavy. When we move it, the antenna goes up on the top in what we call the stowed position. So the center of mass is more center and it's all more stable. If we were to try to drive it with the antenna in the deployed mode, I don't know, it might tip and... So yeah, no, we haven't done it. And we also have levelers. Maybe hard to see, but there's some legs that come out and level the whole truck. So that way you have 0-degree elevation flat.
How much does the panel weigh?
Fully populated with all the electronics? Sure, I'd say 200 pounds maybe.
Oh, okay.
Yeah, it's a little bit heavy, but not crazy.
Another basic question. Did you need to design it to be able to rotate, or could you have a stationary fixed?
We can do both. We can have stationary scans or rotate it, but intentionally we designed it to be able to rotate.
Just wondering if you could design a 2D array to image or sample an entire three-dimensional without ever rotating.
Gotcha. Yeah, you can. So the planar phased array can scan a 90-degree sector. If you want 360, you make 4 of them. Too much for a mobile truck. There's also the concept of a cylindrical type array. We have one of those too. It's fixed. You can make what they call a conformal array, some kind of phased array on the surface of a sphere. All of these concepts sound really cool and great, very hard to fabricate and make them. I'm looking at Eric and he's like thinking, ooh, I don't know. But planar is easier to make, it's more practical. And yeah, 4 faces would be great, but cost of one is already kind of high, so we're trying to just do with one.
Danny.
I think the way you've been scanning it, you may have had reduced sensitivity, but I'm curious if you think that it's possible to see clear air return.
Oh yeah, definitely. I mean, at not too far ranges, yeah, we can see clear air for sure. And if we do pencil beams, we definitely see clear air. The sensitivity goes down as you spoil the beam or you change it. You're just spreading the same amount of power over wider angle. So if you do some spoiling, but not too much, you know, if the beam is 3 degrees and you take it to 5 or 6, okay, you lose a little bit, but not too much. If you do one of these two-dimensional spoiling 20 by 20, that's a huge reduction.
Means the clear air could be either it is a drag scatter or could be insect scattering, which you are talking about. Which one?
We've seen insects and we see clear air velocities. We can measure Doppler in clear air. We haven't tried to get bragg scatter.
Okay.
We've done bird bath scans as well, not in clear air, but it's another way we verify calibration is we just point vertically up and scan. And then you want the ZDR to be approximately 0 at broadside, seeing spherical raindrops. As you go off the broadside, you know, maybe you see something else. But there's some math to correct for that.
Thank you. If there's no other questions, David will be here tomorrow. If you have questions, please send me an email or he's in room number 2014 across Dixon's office here.
Yeah, and here's my email. Oops, in the last slide. You can email me if you want to talk more. We can chat more today. We can chat tomorrow. Or later. Set up a virtual meeting some other day.
Thank you very much.
Thank you.